Thanks, guys. Sorry, I'm trying to figure out if there's anything I can do that's going to make this work any better than before. I'm happy to keep persevering, but I'm just wondering whether it's better to just leave you guys with my pre-recorded videos that at least, even if they're not as detailed as I wanted it to be today, they are there and the sound works okay. But I'll give it a go. So we got as far as the Dalton model, and we said that the Dalton model said that atoms can't be split up into anything that's smaller. And then J.J. Thomson came along and he had the plum pudding model. He discovered the electrons, and he said that it was kind of like, it's like a Christmas pudding. So it was a big ball of positive charge with the electrons scattered throughout it. Oh my god, thank goodness. Right, let's roll. Okay, so then we got as far as Ernest Rutherford, and he is the first person where you actually need, well, he's the only person where you need to know the experiments that he did. So he and his students, Geiger and Marsden, carried out something called the alpha scattering experiments. They took a really thin sheet of gold foil, and they fired alpha particles through it. So an alpha particle is just like a helium nucleus, so like helium that's had the electrons pulled off it. And they found that when they did this, most of the atoms went straight through, and this was evidence for the fact that most of the atom was empty space, which they didn't know before. But then also they found that some of the particles were deflected, and this was evidence for the fact that the mass was concentrated in a positive nucleus. So then we had the Bohr model. This came up last year, and people didn't know what it was called. So basically, as soon as you have electron shells, we start calling that the Bohr model. And then in about 1920, a number of different groups of scientists all started independently using the word proton. So we don't actually know who invented them, but that was the point where we started knowing what atomic number was and being able to define things in terms of their numbers of protons. And then finally in 1932, James Chadwick came along and he discovered the existence of the neutron. And this was really important because it helped us to explain some mass data. So if you imagine, there are things like chlorine that have a non-integer mass. They have a mass that's not a whole number, and we didn't know why before, but suddenly we could actually start to figure this out. In answer to the question, it's got to finish by 5 come hell or high water, because I have places to be. So it's going to be a bit of a squeeze, but I'm going to do my best. Okay, so next up we get to the periodic table. So you should know that your periodic table that you are going to get given in the exam, it has a key with it. And it can be separated out into groups, which are the vertical columns, and periods, which are the horizontal rows. So the vertical columns, the groups, they are based on how many electrons something has in its outer shell. So anything in group 1 has 1 electron in its outer shell, and so on and so forth. And then the periods are based on the number of shells. So this here that I've highlighted is period 4. Everything that is in period 4 has 4 electron shells. We can also divide our periodic table up with a bit of a staircase, which might be there or might be there depending on who has taught you. Either one of those is absolutely fine. And the reason that they're absolutely fine is that in GCSE, we don't study the things that are very, very close to that line. So we call them the semi-metals or the metalloids, and we just don't study them. What we do study are groups 1, 2, the transition metals, 6 and 7. So 1, 2 and the transition metals are all examples of metals, and then 6 and 7 are examples of non-metals. The one to watch out for is that hydrogen is kind of floating around here at the top, not in a sensible place at all, and it's that's a non-metal. So just watch out for that one. Now, we define metals as being things that form positive ions, and then we can also say that they are malleable, which means they can be hammered into shape. They conduct both electricity and also thermal energy, and then they also have high melting points. So the periodic table hasn't always looked like it looks now. So it started out as just a simple list of elements based on their atomic weight. And then we've kind of progressed since then. So to begin with, it was incomplete because actually not a lot of elements had been discovered, for the reason that to discover an element, you need it in its elemental form. And most things are going to react with other elements in order to form compounds. So that meant that the early versions of the periodic table were missing lots and lots of elements. Now, whereas for the atoms, you have lots of different scientists you need to know about, here the one you need to know about is Mendeleev. So Mendeleev developed his periodic table, and he did three key things. One was that he switched around some groups of elements that just didn't make sense to him. So at that time, alkali metals and noble gases and things we weren't fully up to speed with. But just to give you an example, if you look at your periodic table, then you can see that potassium has an atomic weight of 39 and argon has an atomic weight of 40. So that means if we were going to put them in order of weight, then we would put potassium before argon. So we would put potassium, which is a super reactive metal, in with the noble gases, which just doesn't make sense. So that was one thing that he did. Second thing was that he left some gaps. So he recognised that they probably hadn't found all of the elements. And then the third thing was that he made predictions about which elements should go in those gaps. So he said, there's going to be an element, we haven't found it yet, but when we do, it'll have a melting point of this, it'll have a density of this. And he made those predictions. And when it turned out that his predictions were right, then that was very good evidence for other scientists to accept his periodic table. Right, 10 seconds for me to have a drink of water, just because I'm really bad at drinking during these things, and then I lose my voice. Right, next up, you need to know about different parts of the periodic table. So if you're doing combined science, you need to know about the alkali metals, the halogens, and the noble gases. And if you're doing triple science, you also need to know about the transition metals. So alkali metals first. So we know that these are very, very soft, particularly when compared to the transition metals. So they're so soft that I'm actually able to cut this one with my scalpel. They all have one electron in their outer shell. And when they undergo chemical reactions, they lose that electron. It's easier to lose the electron when it's further away from the nucleus because it's experiencing less electrostatic attraction to the nucleus. So the larger the atom gets, the more reactive it is. Now that is only true for metals. And here we're talking about the alkali metals. So as we go down the group for the metals and we add an extra shell, then the elements get more reactive. So that means that potassium is much more reactive than sodium, and sodium is more reactive than lithium. When these metals react, they can react with oxygen to make metal oxides. They can also react with water to form metal hydroxides, which are alkalis, which you can test for with a universal indicator or another pH indicator like litmus or phenolphthalein. And they also make hydrogen gas, which you can ignite or set fire to prove that it's hydrogen, because it will burn rapidly with a squeaky pop sound. The alkali metals also react with chlorine. So chlorine is a green gas, and when they react, that green gas disappears, and instead we get this white solid, which is a metal chloride. And it's also a very exothermic reaction, so we see a very bright light as the green chlorine gas disappears. So here's just an example of it happening. So as you can see, we need to heat up the sodium, and it's got that orangey yellow flame that you're expecting if you're a triple scientist person and you know about that. And then when we put the gas jar of chlorine over the top, then you can see that those white crystals being formed, that salt being formed, and after a little while they will fall down to the bottom and you'll be able to see them as salt. Okay, so next up we've got the group 7, which is the halogens. So this is still for combined scientists as well. So because these are in group 7, they have 7 electrons in their outer shell. They all form diatomic molecules, which means molecules consisting of 2 atoms with a covalent bond between them. And because they all have the same number of electrons in their outer shell, they're all going to form molecules in the same way. So chlorine is one of your named examples of a molecule, but in the past few years, AQA have also asked about iodine, they've asked about fluorine, and people have panicked because they haven't studied those ones. But you know that they're all going to have the same outer shell electron conformation. In terms of their reactions, we can think of them as being kind of the opposite to the alkali metals. So whereas metals get more reactive as you go down the group, non-metals get more reactive as you go up the group. So this means that the elements that are higher up in the table are able to displace the ones that are lower in the table. Yes, metal chloride is a type of salt. All ionic compounds are salts. Yes, everything we've done so far has been combined. We're about to get to some triple, and at that point the header at the top of the screen will go green. Right, so this is where I'm going to show you that you can displace halogens from their compounds using a halogen that is higher up in the table. So here what I've done is I've put some salt solutions in the spotting tile, and then I'm going to add the halogen solutions to those. So there's a water control on the left hand side, and that shows me what it kind of should look like if there's no reaction. And then you can see that in the top row, the chlorine has managed to displace the bromine and the iodine, and then the bromine has been able to displace the iodine as well. Okay, so in terms of their states, as we go down the group, the atoms get larger, and therefore the molecules that they're made into get larger, and therefore the weak intermolecular forces between them get stronger. And that means that whereas fluorine and chlorine are gases, bromine is a liquid, and iodine and astatine are solids. Next, we've got the noble gases. So these are the last ones that you need to know about if you are if you're doing combined science. So the noble gases, that word noble means inert or unreactive, and that tells you what the key characteristic of that group is. Now, the reason that these elements are unreactive is because their atoms have got a full outer shell. So when atoms undergo chemical reactions, they exchange electrons to find a really stable configuration, and a full outer shell is one of the most stable configurations that there is. So because these elements already have a full outer shell, they don't need to undergo chemical reactions, and so the noble gases don't usually form compounds, and that makes them really useful for situations where you're trying to stop a chemical reaction from happening. So for instance, if you have a light bulb and that metal filament gets really hot, then if it was just full of air, then the metal would react with oxygen and the filament would break. But if you fill that light bulb with argon instead, or helium or something, then the noble gas won't react with the metal filament, the bit that's actually glowing, and so the light bulb will last a lot longer. You do also need to know about the physical properties of these noble gases. So just like we said with group 7, as you go down the group and the atoms become larger, there's a stronger interaction between them. That is harder to overcome, it needs more energy, and therefore the boiling point of these noble gases becomes higher as we go down the group. Don't be confused by the fact that because they're negative numbers, it doesn't look like it's getting higher. It is taking a higher temperature to boil those noble gases. Oh, there's my weak intermolecular forces. Right, okay, so you can see at the top here, this has gone green. That is your signal that this slide here is just for the triple scientists, but it's only one slide, so don't go too far away if you're a combined scientist. So the transition metals, are the metals that sit between group 2 and group 3 of the periodic table. There are a bunch of named examples, but to be honest, you don't need to know them because you have the periodic table, right? So you can look at this and see in the exam. So in comparison to group 1, the transition metals are harder, they're denser, they have higher melting points, and they're far less reactive with oxygen and water and halogens like chlorine. You don't need to know anything about oxidation numbers. You do need to know about ion charges, but we're going to get to them. And the colours of the displacement reactions is paper 2, so we're not covering it today. So there are 3 particular things that you are supposed to know about the transition metals: that they form ions with different charges, that they form coloured compounds, and actually the colours of those compounds correspond with the different ion charges. And then also they're useful as catalysts. So they could sort of say to you, oh, this reaction has a catalyst, which one of these elements is most likely to be it? And you would be looking for the transition metal. Okay, so now we're on to our bonding topic. So everything in the universe is trying to become more stable. Now, that doesn't necessarily mean that it's trying, obviously, because atoms don't have thoughts and feelings. But in the same way that if you were standing off balance, you would eventually probably fall over and reach a more stable position. Atoms and molecules are going to behave in a way that makes them more stable. And having a full outer shell is one of the best ways to become more stable, although it's not the only way. Okay, so you don't mean oxidation numbers, you mean charges. So when we get to the ionic compounds, don't worry, we're going to go through it. Another thing you can do is to form stronger bonds. So that's why some things that already have a full outer shell will then go on and do more chemistry because they're trying to get to a different stable conformation. Okay, so we've got 3 types of bonding that we need to know about. First up, nice and easy, is our metallic bonding. Obviously, that's happening between metals. And then we've got ionic bonding. Please note, not iconic and not ironic. And then finally, we've got covalent bonding between the non-metals, and once again, not convalent. Now, I will say that with GCSE Science, your spelling is not going to cost you marks as long as we know what word you're talking about. So there are very, very few examples of pairs of words like alkane and alkene in paper 2. But just, you know, you're trying to give your examiner the best impression of yourself. You want to look like you know what you're talking about, and spelling a really key word wrong is probably not going to give them your best impression. So in terms of which elements are going to do which kinds of bonding, that little staircase that we drew is going to sort us out. Yeah, so far, folks, I've had literally one slide on triple science, so I don't think the combined scientists can compare too much. So, as we said, everything to the left of that staircase is a metal, everything to the right is a non-metal. So, if you've just got metal atoms, you're going to form metallic bonds. If you've just got non-metal atoms, then you're going to have covalent bonds. And if you've got a mixture of each, you're going to have ionic bonds. Folks, I'm going to do everything, but the vast majority of it is in both papers. And then, as we said, hydrogen on its own is a non-metal. Okay, so we've said that these atoms are uncharged, and the reason they're uncharged is because they have the same number of protons and electrons. Triple is wherever it comes in the spec, folks. It's not like the olden days where there's a whole separate paper. It's sprinkled throughout here. So, when we start having bonding, we might encounter ions, and ions are charged particles made when an atom gains or loses electrons, and that's going to stop it from being neutral, because the whole reason it was neutral is it had the same number of protons and electrons. So if it gains electrons, it will become a negative ion, and if it loses electrons, it will become a positive ion. So that takes us on to metallic bonding. So if we look at a pure metal at an atomic level, we see that it has a giant structure. So giant means thousands or even millions of atoms or positive ions. And it's forming something called a giant metallic lattice. So that lattice is mainly made of these positive ions, and they're in these regular rows. Now, the reason that they're positive ions is that each metal atom has lost its outer shell electrons. So just the outer shell electrons, it's still got other electrons in the inner shells, but it's lost its outer shell electrons, and so the ion that is left behind is positive. So we've got these regular rows, and surrounding them are the electrons that have been given up by each atom. So they're delocalized because they're not tied to one particular atom, and they form this sort of C, okay? So since we've got the positive ions and the negative electrons, they're attracted to each other by this force called a strong electrostatic force of attraction. And this is acting between the positive ions and the negative delocalized electrons, and it's holding the entire metallic lattice together. Why is that page stupid? Okay, so next we need to talk about why it is that that these different metals have particular properties. So firstly, we're going to talk about why it is that they have high melting and boiling points. So we've just mentioned that there's this really strong electrostatic force of attraction between the positive ions and also the negative delocalized electrons, right? So that strong electrostatic force of attraction needs a lot of energy to overcome it, and that's why they have high melting and boiling points. Then we've also mentioned these delocalized electrons, which you can see whizzing along there, and they are able to move and to carry charge through the metal. And it's really important that we're saying through. We're not saying throughout, we're not saying around, we're not saying across, because none of those are going to get us the mark in the exam. It has to be through, okay? So next up, we're going to say that they are malleable. So this means that those regular rows of ions can slide over each other. So here is my regular rows of positive ions. And if this is a pure metal and I hit it with a hammer, then that top row of ions there can just slide straight across. Now, if we compare that to an alloy, alloys are an example of a mixture. So whereas in a pure metal, there are only ions of one size, in an alloy, there are ions of more than one size. Because there's usually a second metal in there, or it could be carbon. Now, one thing to point out here, it's fine if you say ions, it's fine if you say atoms. It's not sufficient if you say particles, because Everything has particles of different sizes because the electrons are very different sizes to the ions. Okay, so you've got to pick atoms or ions, either one of those is fine. So because they're different sizes, this has distorted those layers, and so they can't slide over each other. And this is going to make the alloy much harder. Okay, so we've already said that metals lose their outer shell electrons, but now we need slightly more detail, and we're going to represent this with some diagrams. So the easiest way for this atom to become stable is for it to have a full outer shell, which it could achieve in this instance by picking up 7 electrons, which sounds like a lot of effort to me, or by losing 1. So that's what's going to happen. Our metals are going to lose a single electron. And so because we've lost a negative thing, overall that ion is positively charged. And so we're going to show that that positive charge is spread over the entire ion by using these square brackets around it. So because lithium is in group 1, that's what it's going to do, and we can look at some more examples. So in each example, the metal atom is going to lose electrons until its outer shell doesn't have any left. So if we look at beryllium, you can see it's got 2 electrons in its outer shell, and so it's going to lose both of them, and it's going to have a 2+ charge. And then sodium is also in group 1, so like lithium, it's going to lose 1 electron and have a 1+ charge. And then magnesium is in group 2, so it's going to lose 2 and have a 2+ charge. So that is nice and straightforward. You're always with metals losing electrons until you've got a full outer shell. Now, you should be aware that no single atom is going to turn into an ion just on its own. So those electrons that are lost by lithium and sodium and magnesium, they have to go somewhere. And this is where we're going to need our nonmetals. So the nonmetals are on the opposite side of the periodic table, so it probably won't surprise you to hear that they make ions in the opposite way. They gain electrons rather than losing them. So here we've got fluorine. We know it's in group 7, so that means that it has 7 electrons in its outer shell. And we know that in total it's got 9 electrons and it's also got 9 protons. So at the moment it's balanced. But because it's in group 7, it needs to gain an electron. So here's an extra electron. It doesn't matter whether you draw that as another cross or if you do a dot and a cross. I tend to do dots and crosses because then it's obvious what's come from where. But if you've put crosses for everything, that is absolutely fine. So since we've gained an extra negative charge, we're going to have square brackets again. And instead of having an uncharged atom, we now have a charged ion. So again, we can go through this process. We can say, oh, oxygen needs 2 additional electrons. So you can see them there. I'm adding them and taking them away so it's really clear. And so it's going to have a 2- charge. Chlorine is also in group 7, so it needs 1 electron there. So it's going to have a single minus charge. And sulfur needs 2 extra electrons, so it's going to have a 2- charge. Now, it's really important when you're talking about your non-metal ions that you get their names right. So for the metals, it was easy because you have a lithium atom and a lithium ion. But here you have a fluorine atom, but then a fluoride ion. And that's really, really crucial. If you think you're going to forget, just use the symbol because the symbol is fine. If you put F-, that is absolutely allowed. But you can't have an oxygen ion. It's an oxide ion. And then likewise chloride and likewise sulfide. And so you need to get those right. Okay, so if we actually look back at the periodic table, we can make predictions about the type of ions that a particular element will make. And I think this is kind of what people are talking about in the chat. So I always say to my classes, you go into the exam, you're feeling super positive because we've done final prep and it's hopefully gone more successfully than the start of this live stream did. So you go in feeling super positive, and the first thing you're going to do is in the top left of your paper, you're going to write a plus because you're feeling so positive. And then you're going to go, oh, great, I did exactly what Dr. De Bruin told me to do. So I'm feeling even more positive. So they put 2 pluses on the next one. And then over on the right-hand side of the table, we have 2- for group 6 and single minus for group 7. So if you're taking an element from one of those groups, then you know exactly what the charge on those ions are going to be. Anything other than those, like any of the transition metals, they are going to have to tell you. You are not expected to know what the other metal ions are going to be. Okay, so very, very common short extended response question asking you to describe how one element reacts with a different element. And one thing I would say here is it's really important that you're using the word atom. Very often we see pupils saying lithium loses an electron, which is true, but what you need to be saying to get the mark is a lithium atom loses an electron. So here, this is a nice easy example because the lithium atom needs to lose 1 and the fluorine atom needs to gain 1. So that's going to go over there. This is going to become negatively charged because it's picked up an electron, and this is going to become positively charged because it's lost an electron. So we're going to say the lithium atom loses an electron and it makes an Li plus ion, and the fluorine atom gains an electron and it makes an F minus ion, or a fluoride ion, and that's all you need to do. Likewise, beryllium is in group 2, oxygen is in group 6. So here we would have our beryllium atom giving up both of those outer shell electrons. So we would have an oxide ion with a 2 minus charge and a beryllium ion with a 2 plus charge. So again, the beryllium atom loses 2 electrons, it makes a Be2 plus ion. The oxygen atom gains 2 electrons, it makes an O2 minus ion, or an oxide ion. Now, it starts getting more complicated when the numbers of electrons that need to be lost and gained don't match up. So at this point, we would be saying that we've got 2 lithium atoms that both lose 1 electron, and this makes 2 Li plus ions. And then the oxygen atom gains 2 electrons, it makes an O2 minus ion. So I would know, I could either look at diagrams, quite often they give you diagrams in the exam, or just the fact that lithium is in group 1 means that it's going to lose 1 electron, and oxygen being in group 6, it's going to need to gain 2. Okay, so you can figure it out from that. Now, this is where I think people were asking me about things. So let's say that in an exam, they ask you to give the formula of a particular substance. We know that in a compound, the positive and negative charges must equal each other. So if you're a mathsy brained person, what you're doing is looking for lowest common multiples. If you're not a mathsy brained person, hopefully we can get you there anyway. So if if they're going to give you transition metals, by the way, they have to tell you. So the first couple of these you would know, but the bottom couple you wouldn't. So for instance, sodium chloride, right? Sodium has a plus charge, chloride has a minus charge, they balance out. So we just have sodium chloride. But if we took sodium and the oxide ion, then 1 sodium wouldn't balance out that oxide ion. It's not big enough, it doesn't have enough charge. So we would need Na2O, so that my 2 pluses balance out my 2 minuses. Likewise, magnesium oxide, 2 plus balances 2 minus, that's okay. But if I was going to have that nitrate ion in there, I would need 2 of them to balance out magnesium. And because it's a compound ion, I have to use brackets around it. Now, some of you might have been taught the crossover method. So if you haven't, the idea of the crossover method is that you take the charges and you use those as your little numbers down the bottom. So the 5 goes there, the 2 goes there, and we get V2O5. Now that is perfect, right? That works really, really well. The reason I would be a little bit cautious about it, well, there's 2 reasons. One is this. So based on that crossover method, as I've just described it, we would get V1Cl5. And we never do that, right? Chemists are lazy. We do not write the number 1. Okay, so instead we should be writing VCl5. So that's the first thing that you just need to be a little bit careful about. Do you understand that the number 1 is never coming up in a chemical formula? And then the other reason is a situation like this. So based on that crossover method, you would think it should be Mg2O2, but it's not, because the whole point of this ionic compound formula is it's the simplest possible ratio. And 2 to 2 is not the simplest possible ratio. It should be 1 to 1. So we're going to have MgO. So I would say that crossover method is really useful to have in your back pocket, particularly if you're panicking in the exam. But just bear in mind that what you're actually going for is the simplest possible ratio, and you're never going to write the number 1. Okay, so then we need to talk about the properties of these ionic compounds. So when you've got a covalently bonded substance, it might only have 2 or 3 or 7 atoms in it. But an ionic compound is a giant structure. So it's got these thousands or even millions of ions, and that's going to lead to it being a solid at room temperature because of the strength of the forces between those ions. So in this, we're going to have our positively and negatively charged ions in a constant ratio. So that means it might be 1 to 1, like this picture. It might be 2 to 1, which I can't draw because it's too hard. But whatever the ratio is, it's always going to stay the same. And then because we've got a positive and a negative thing being attracted together, we're going to have a strong electrostatic force of attraction acting in all directions. Now, you might be asked about different ways of representing this structure, and both of these ways have got some disadvantages. So the first thing is that neither one of them shows that this is a giant structure with thousands of ions, right? It's just not showing that very, very clearly. And then secondly, the one on the left is a 2D drawing. It makes it look like this is a 2D thing, and it's just not. And the one on the right, it has these sort of sticks in there, and that kind of makes it look like these bonds are things that you can just like touch and grab, and that's not true. The audio keeps cutting out. Okay, I'm not going through this again. Well, I'm just going to keep going and do what I can. Okay, so typical exam question might ask you why ionic compounds are solids at room temperature. You would talk about the fact that they have got a giant ionic lattice structure. You talk about the fact that there is a strong electrostatic force of attraction between the oppositely charged ions. That's a really useful phrase for you to have because very often it's worth 3 marks on its own. 1 for strong, 1 for electrostatic force, and 1 for describing what the force is between. Every ionic substance does form a giant ionic lattice. Thanks, guys. I was getting stressed. Cool. So that strong electrostatic force takes a lot of energy to overcome, and there's just not enough at room temperature. So therefore, these ionic substances have got high melting points and high boiling points as well. So room temperature is not giving enough energy for that to be overcome. Next thing we might be asked is why don't ionic substances conduct electricity as solids? So we should know that current is the movement of charged particles. Now here's a really important thing. It says charged particles. It doesn't say electrons. So 99% of the time in physics, you're talking about electrons. So people think electrons are the only thing that can move. When you're talking about ionic compounds, you are not going to be talking about electrons. You're going to be talking about ionic bonding. Jake, I love that you think that this is sufficiently well produced to be pre-recorded. No, I'm very much live and quite stressed right now. Okay, so ionic compounds are made of these charged particles. They're made of these ions. They are charged, but we just said that it was the movement of charged particles. So the point is that they can't move because they're held together by this strong electrostatic force of attraction. And until that's overcome, they can't conduct electricity. Okay, so then why do they conduct electricity when they're liquids? Well, we've just said current is the movement of charged particles. So when the compound is melted, or when it's dissolved, that strong electrostatic force of attraction is overcome and the ions are free to move, and off they go like that. Okay, more water. Cheers, guys. I appreciate the support. Okie doke. So we just said that when a metal reacts with a non-metal, the non-metals need to gain electrons. So when lithium bonds with fluorine, the electron is given from the non-metal to the metal, right? You can think of it like the electrons are always moving left to right across the periodic table. And so we get our ions like this. However, if we've got 2 non-metals bonding together, then that's no good, right? We can't have one non-metal giving its electron to the other non-metal because then it would be missing 2. So instead, what needs to happen is that the 2 atoms are going to share a pair of electrons, and that's what we're going to call a covalent bond. Now, as GCSE chemistry, you need to be able to draw 8 named examples of small covalent molecules. Yes, I will cover the required practicals, but as you can see from the thing at the top, we are in Unit 2, and the first required practical doesn't come up until Unit 3. Okay, so first up, we've got hydrogen. Now, I always used to say that they would give you the circles and just ask you to fill them in, because every other year they have, and then last year for the first time, they asked you to draw it from scratch. So just be aware of that. But basically, if you're not going to go on to A-level and you don't really need to understand this, the easiest way to get through tomorrow's exam is to know that wherever you have one of these overlaps, you're going to put a dot and a cross. And the only exception is oxygen and nitrogen, because they're the weird ones that we'll get to at the end. And then apart from hydrogen, you're just going to make sure that everything else has access to 8 electrons in total. It's all right. You're just like the 15th person to ask it. Okay, so hydrogen, dot and a cross, you're done. Chlorine, dot and a cross, and then make sure that this atom has got 8 electrons in total, and this atom has got 8 electrons in total. Simple. So we're only ever doing with these, by the way, the outer shell electrons. We don't need to draw all the extra ones inside. Then hydrogen chloride, dot across, and then make sure that chlorine has got 8 in total. The hydrogen, we don't need to add any more because hydrogen's only got 1 shell, so it can only fit 2 electrons in. So it's already got as many electrons as it can take. Then methane, dot across, dot across, dot across, dot across. If you count them up, then the carbon in the middle now has 8 electrons, so that's fine. Ammonia, very similar, dot across, dot across, dot. Hold on, however many 3 was, I lost count. But then if you look at that, that's only 6 electrons. And also nitrogen has only used 3 out of its 5. Okay, so yeah, my dot in the middle is a nucleus. You can also do it with, like, you could write the N's and the H's, that will be fine as well. You can do it with a dot, it doesn't matter. AQA are very not picky about it. Then we've got water, so dot and across, and to get oxygen up to 8, you can have 2 more lone pairs. If you missed Unit 1, just scroll back in the live stream. Or there is also the pre-recorded videos that I've done. They're like the most popular thing on my channel, so if you just click on the channel name, you'll be able to get to them. Now, oxygen is where it gets weird, right? Because oxygen has got a double bond, so we're going to need dot cross, and then 2 lone pairs on each molecule. And then nitrogen is really weird. It's the one example of a triple bond that you're meant to know about. So it's going to look a little bit like that. Okay, so they are your 8 named examples of small covalent molecules. We did also say that they can just ask you about something random from group 7, because you're supposed to know that everything in group 7 reacts in the same way and bonds in the same way. So even though we've only done chlorine, you could do exactly the same diagram for fluorine or iodine or whatever else. Okay, so there are some other ways that we can represent these small covalent molecules. We can use those full dot and cross diagrams. We can use displayed formulae like this, and this is more common particularly for quite complicated molecules when we're just trying to make it a bit easier to understand. But for each one of these, rather like our giant ionic lattices, we need to be able to describe some good things and some bad things about these different ways of describing them. Quantitative is Unit 3. Yes, there were many issues at the beginning. I'm very sorry. Okay, so first one, the displayed formula is very, very easy to draw. Okay, so it's going to make life simple for you. Second thing, the dot and cross diagram and the displayed formula and the Lewis formula, incidentally, you're not supposed to know it's called a Lewis formula, but it's really hard for me to be like that one when I can't physically point. So those 3, they all make it look like the molecule is 2D. And we know it's not, right? It has a 3D shape. So that's a good thing about this ball and stick model. And then also the dot and cross diagram and the Lewis diagram both make it really clear that, that the bond is just shared pairs of electrons. Whereas that ball and stick model, again, makes it look like a physical thing that you can reach out and touch. And that's just not accurate. Okay, so with these small covalent molecules, you also need to be able to talk about their properties. So the first thing is that they've got low melting and boiling points. So in order to explain this, we need to talk about the forces that are holding the individual particles together. So between these 2 methane molecules, there is a force called a weak intermolecular force. And if we compare it to the strength of a covalent bond, even the strongest intermolecular force is only about 10% of the strength of that covalent bond, right? So that's why we call it weak. So in order for those methane molecules to separate and methane to be a gas, that weak intermolecular force needs to be overcome. And it doesn't take very much energy to do it because it's so weak. So we heat up that methane, and the weak intermolecular force is overcome, and then they can separate out like that. So at no point did we have to break the strong covalent bonds, right? They did not break, because if they did, it would take a lot more energy and the melting point would be a lot higher. And then in order to understand why they aren't conductors, again, we talked about the fact that current was the flow of charged particles, but this molecule overall is uncharged, right? There isn't any overall electrical charge, therefore it can't conduct electricity. I can turn my mouse into a laser pointer, but to be honest, there is so much else going on at the moment, I'm just not going to even try. Okay, so these weak intermolecular forces that we just mentioned, the size of them is directly related to the size of the molecule. So methane has a boiling point of about 162 degrees C, whereas this is butane, which is very similar but bigger. And because it's bigger, it has slightly stronger intermolecular forces. And so that doesn't boil until -1. Should we all say yes? Overcome is my favourite word of choice. That's the word they tend to use on mark schemes and things. If you said break, that would be fine as well. Yeah, they do tend to allow it doesn't contain any delocalized electrons. I don't like it because there are lots of things that conduct electricity that don't have delocalized electrons either, but they have put it in as an allow statement for the last couple of years. So yeah, don't panic if you do end up writing that. Okay, so I was saying here about how as the molecules get bigger, the weak intermolecular forces get stronger, and so the kind of obvious endpoint of that is when we start thinking about polymers. So a polymer is a very long chain of repeating units called monomers. If you have ever been taught by me, you've heard me wax on and on and on about how important that word very is, okay? So those monomers, they're not individual atoms, they're actually small covalent molecules that have then formed covalent bonds between them to make these very long chains. So within one chain of a polymer, there are strong covalent bonds that I've labelled there, and they're sharing pairs of electrons. And then within one chain and the chain next to it, there are these weak intermolecular forces. So they're exactly the same ones that were between those methane molecules. They're just massive because it's such a massive molecule. And so therefore, polymers tend to be solids at room temperature because the molecules are much, much bigger than ammonia or oxygen or chlorine. You know, they're literally thousands of atoms long. You should also be able to recognise polymers from this way of drawing them. So you come up as like a little 1 mark tick box kind of thing of like which of these is a polymer, or what type of substance is this. So polymers is paper 1. If you're doing triple, then all the extra detail about thermosetting and thermosoftening and different reaction conditions, that's all paper 2. And addition polymers and condensation polymers, that's paper 2. But the combined scientists just need to know that a polymer is a very long chain, blah, blah, blah. That is paper 1. That is structure and bonding. Yes, it is part of unit 2, exactly. But for some reason, my headers have gone crazy, so it's currently saying unit 1, but yes. So you should be able to name them. So if we've got a monomer that is chloropropene, then the polymer will be polychloropropene. And also you should just be able to recognise the ways of drawing them. So if the N is at the start, it's the start of the reaction and you've got monomers. If the N is at the end, it's the end of the reaction and you've got a polymer. And also you can see that you've got the bonds coming out the side of the brackets. Yeah. Oh no, stop texting me. Okay, so then we move on to our giant covalent structures. So whereas a small molecular substance contains just a few atoms bonded together, a giant covalent structure might have thousands or even millions of atoms all joined together by strong covalent bonds. So 3 examples that you need to know about are diamond, graphite and silicon dioxide, or it's also called silica. So these are all solids with high melting points because with these ones, you actually do need to break those strong covalent bonds in order to melt them. And that takes a lot of energy. So first up, diamond. It's made from carbon. In every one of the carbon atoms is bonded to 4 other carbon atoms, and so you can't separate out one atom without breaking the bonds. Okay, so the whole of the diamond is one big molecule. No, so silica is silicon dioxide, so it's a compound containing silicon and oxygen, whereas silicon is just the silicon element. I'm going to get to electrolysis, don't worry, it's unit 4. We'll get there. Well, not soon, but at some point. Yep, so diamond, very hard, very high melting point, can't conduct electricity. Right, here we go. Here is silicon dioxide, aka silica. So the blue circles here are silicon, and then the black ones are oxygen. So silicon dioxide, which is also called silica, contains silicon, but it's not the same thing as silicon. So very similar to diamond, lots of strong covalent bonds, so it has a high melting point and it's hard and it can't conduct electricity because it doesn't have any charged particles. Right, next up, graphite. AQA love to ask you to compare graphite to diamond for the reason that they are both made of carbon. And it still has a high melting point because it still has lots of strong covalent bonds. but this time every atom is bonded to 3 other carbon atoms. So you get these layers of hexagons, and you're going to have 1 spare electron left over because it's only making 3 bonds instead of making 4 bonds. And so this means that it can conduct electricity. So rather like we said with the metal, the delocalized electrons can move through the substance. It needs to be through, not throughout, not around, not across. The delocalized electrons can move through the substance and carry charge. No, I don't think they would ever say silica without clarifying that they meant silicon dioxide, because silicon dioxide is the wording that they use in the exam. It's just not what every other human in the universe calls it. And then because there aren't bonds between these layers, the layers can slide over each other, and that makes graphite soft and slippery. So yes, we can also take just 1 layer of that graphite and we can make something called graphene. And this is it's just a single layer of graphite, and people were kind of really hopeful that it would be this sort of wonder material because it can conduct electricity, but it's also much more flexible. So it's less brittle than graphite, and you can use it in electronics and also composites. I don't make predictions because you can't in science, and I'll see if I can get onto the diatomic single atom thing, but it doesn't really make sense outside of the context of Unit 3. No, this is everything that is on the spec. That's why it's 3 hours long. Okay, so, wrong. So it's up for debate whether we're going to call Fullerenes a giant covalent structure or not, because it's not really very giant. This one is Buckminster Fullerene, and it's only got 60 atoms in it, but it is another way in which carbon can bond. So it's usually hollow balls or tubes, usually based around hexagons, although sometimes they are rings of 5 or rings of 7. So Buckminster Fullerene is the most famous one because it was the first one to be discovered. You are supposed to know the name of that. How do I identify the interconnected forces and covalent bonds? So that the only giant structures you know about are like named examples from the spec. So silicon dioxide, diamond, graphite, they are things that you know about. Anything other than those, if it's covalent, so it's all non-metals, it's going to be a small molecular substance. We will go over fuel cells as long as I don't run out of time. We've still got 2 hours. Hopefully we can make it. I've totally lost my train of thought. So Fullerenes also include nanotubes, which are these very, very thin tubes. They've got a very high length to diameter ratio and a very high strength to weight ratio, which makes them really useful in nanotech and electronics and also material science. Right, second bit of triple of the whole thing. Yes, you do need to know the half equations for fuel cells. But first, you need to know about nanoparticles. So again, last year they specifically shouted out that people did not know that a nanoparticle was a few hundred atoms. Particles can be defined according to their size. So nanoparticles are smaller than fine particles, which are in turn smaller than coarse particles. So a fine particle is 100 to 2,500 nanometers across, and then coarse particles are 2,500 to 10,000 nanometers across, and they're also called dust. Gina, you can keep on asking me, but I'm not going to talk about it until we get to Unit 3. So dust is a technical term. You're not just saying like it's a bit dusty in here. So these very small particles are advantageous because they have a really high surface area to volume ratio. So if you take a cube and you cut the length and the width and the depth in half, then you end up doubling the surface area while keeping the volume the same. So this really high surface area is really useful because it means that you can use a lot less of the substance, especially if it's acting as a catalyst, and that makes it a lot cheaper. Sometimes you'll also find that nanoparticles have completely different properties compared to the substance when it's bulk. Difference in uses between Fullerenes and nanotubes. Nanotubes, you're thinking more about sort of construction of composite materials, things like making tennis rackets and things. And Fullerenes, you're thinking more about material science and also getting drugs into cells. Yes, you should know the numbers. Okay, hydration stations. Okay, we're on to Unit 3. So First thing that you need to know, whether you are doing combined or triple or foundation or higher, everyone needs to know that the law of conservation of mass tells us that no atoms are lost and no atoms are made during a chemical reaction. So therefore, the mass of the products has to equal the mass of the reactants. And that means that you can represent any chemical reaction with a simple equation, which is going to be balanced in terms of the number of atoms of each element involved on both sides of the equation. So if you look here, I've got 6 carbon on the left, I've got 6 carbon on the right. Now, where people tend to fall down is not that they don't understand that, it's that they're not very good at interpreting symbol formulae. So apologies if this is massively patronising to people who do get this, but we're just going to look at it anyway. So first thing, that big number at the front, that is what we call the coefficient. And I'm going to keep using that word throughout this topic. And that applies to everything that comes out after it. So this means 4 of everything in that main formula. So the little number at the bottom, the 2 next to the aluminium, tells me that there are 2 aluminium atoms. It's absolutely vital that it's at the bottom. It's a subscript, not a superscript. It's not a squared sign. You will not get marks if you write a squared sign in your exam. Then inside the bracket, we've got 1 sulfur atom and 4 oxygen atoms. And then that bracket covers all of that. So if the little 3 was just next to the oxygen, it would just apply to the oxygen. But because of the brackets, it applies to everything in the brackets. So that's going to mean I've got 3 sulfur and 12 oxygen. And then we said that the 4 at the front applies to everything. So that would therefore give us 8 aluminium, 12 sulfur and 48 oxygen. I mean, it would really depend on what the question was about nanoparticles. Most likely things are, what is a nanoparticle? So saying, oh, it's a particle that contains a few hundred atoms, or asking you to tick a box, say how big is a nanoparticle, or asking you about the properties of nanoparticles, or asking you about why they're better than using bulk things. So things like the fact that you can use a lot less of it. Sometimes about it being transparent. There's been a question recently about them being used in self-cleaning windows, so the fact that because they're nanoparticles, you can still kind of see through them. Why can't we just add a number at the bottom of the element to balance it? Oh, good question. Sorry, it took me a second to figure out what you meant. So when you're changing the little numbers at the bottom, that's changing what the chemical is. So like if I have O2, that's regular diatomic oxygen that you're breathing in all the time. If I change that 2 to a 3 and make it O3, that means ozone. It's a totally different chemical. So you can't change the numbers at the bottom when you're balancing things. Okay, so balancing. First thing that you're going to do is you're going to count up how many atoms of each element there are on each side of the equation. Next, you're going to think about the lowest common multiple of each pair of numbers. So you ideally want to start with pairs of numbers that aren't factors of each other. Sorry, that's a horrible sentence, but like here, I'm going to start with the 2 and the 3 instead of the 1 and the 2, just because it's going to make my life easier. So lowest common multiple of 2 and 3 is 6, right? So I need to have the same number of atoms on both sides, and I can't just go adding random numbers. So I'm going to make there be 6 of each. So then I'm going to think, what do I need to multiply my current numbers by in order to get 6? So 3 I would need to multiply by 2, 2 I would need to multiply by 3, and those numbers are going to turn into my coefficients at the top. Right, so I've done that now for one element. I've done it for oxygen. And then I'm going to count up, what have I got now? So obviously I've changed both of those to 6, but also my oxygen on the right, my iron on the right has also changed to 4. And then I'm going to do the same thing again. Now, what's the lowest common multiple of 1 and 4? Oh, it's 4. So I don't need to multiply by anything on the right. On the left, I need to multiply by 4. So that 4 is going to be my new coefficient up there. If something says C70, then that's talking about a fullerene, and it's a fullerene that has 70 carbon atoms in it. Okay, so as well as meaning that equations need to balance, conservation of mass also means that the mass of the reactants has to be the same as the mass of the products. So if I've got an equation like this, I can say that however much the stuff on the left weighs, the stuff on the right has to weigh the same amount, it has to have the same mass. So then I can just do a little subtraction to figure out what mass of water is being made, okay? Now, this starts to get a little bit more complicated when we start thinking about reactions that involve gases. Okay, so let's say I take 6 grams of magnesium and I burn it in oxygen. On my balance at the start of the reaction, it would have said 6 grams because that was how much my magnesium had a mass of. But after it's reacted with the oxygen, I'm going to be left with 10 grams of magnesium oxide. Now, that hasn't just magically got heavier. It's that the oxygen that was in the atmosphere has now been bonded to the magnesium and it's pushing down on that balance. So the reaction appears to get heavier if a gas is a reactant. And then if a gas is a product, then it's going to appear to get lighter. So here I've got calcium carbonate, heat it up until it thermally decomposes and some carbon dioxide would be made, and crucially it would escape. If I did this in a sealed box so the carbon dioxide was locked up, then it wouldn't get any lighter. But because that gas has escaped into the atmosphere, then it would get lighter. You've missed about the first half, but don't worry, because there's a pre-recorded version of this that I did many years ago, so you can go back and watch Unit 1 and Unit 2 afterwards. Okay, on to some calculations. So the relative formula mass is the mass of a particular substance of 1 mole of that substance. And the way that we're going to work out this is just by adding together the relative atomic masses from the periodic table. I don't know what you mean, so I'm not answering that. So here, sodium has got a mass of 23, and there are 2 atoms of sodium per formula unit of sodium oxide, so 2 lots of 23. Oxygen has a mass of 16, so plus 1, 16, gives me 62. Now, you could also be asked to use some math skills and say, what is the percentage by mass of sodium in sodium oxide? So then I would need to say, well, what's the mass of sodium divided by what's the mass of sodium oxide? And then I need to turn it into a percentage by timesing it by 100. Yes, I think it does end up on YouTube in full, but also after the biology, it seemed to take it until like the next morning to upload it. I have no control over that. I think it's just because it's such a big file. So here I would be doing 46 because there are 2 sodiums in sodium oxide divided by 62, and I would get an answer of 74%. So AR is what we use when we're talking about an element, and then MR is what we use when we're talking about a compound or also a molecule. So functionally, they are the same thing as each other. We just give them different names depending on the situation. So if you wrote down MR when you mean AR in one of your calculations, it really wouldn't matter. Will there be a stream physics paper 1? Not after all the technical difficulties I've had with this one. Okay, next up, uncertainty. So whenever you make any kind of measurement, there is going to be some uncertainty in it, right? You can't measure an exact number for anything really, because your equipment just isn't precise enough. So when we say uncertainty, we mean the spread of values around the mean. So like if I was going to measure the temperature, I might say it's 19 degrees. Oh, but now it seems to be 20. Now it seems to be 18. So my uncertainty would be 1 degree to either side. So as we said, no measuring instrument is 100% accurate, and we can have errors that are random, but also errors that are systematic. So we skipped our error-y bit at the start because everything was not working and I just wanted to get going with chemistry. But basically, systematic errors are where your equipment is dodgy and it's always out by the same amount, whereas random errors are just kind of fluctuation around the mean, something like temperature that is just changing all the time. So to solve random errors, you take lots of repeat readings, get rid of any anomalies, and then calculate a mean. So say if I had this data from an experiment, I'd go, oh, that one there is an anomaly, because it's very, very different to all the rest of the numbers. So I would get rid of it before I did any of my calculations. So, oh, said that. So we can report how likely it is that that there's sort of a mistake as something we call precision or as percentage uncertainty. But for today, we're just going to worry about the precision. So for this lot, I would cross out 11.3. I would say that is an anomaly. It's no good. And then I would calculate a mean by adding them all up and dividing by the number that are left. And then I'm looking for the spread of values around the mean. So I would work out what the range is, and then I would halve that, and I would express my uncertainty as plus minus, and then that halved range. So reasons for the anomalous result is going to massively depend on the experiment. You're never just going to say human error. It's never a good enough reason to just say, oh, I just wasn't very good at the experiment. So it could be things like changes in temperature will affect your results. If it's an experiment with a gas, there's always something in there about like the gas escaping. If it's something about temperature changes, having not stirred it consistently. Or yes, random error, so just things like the temperature fluctuating in the room. In higher tier and science, almost not true. In higher tier, all of the maths has to be at least a foundation level in order to be counted. There are still things, so then you can't just count adding up numbers as a math skill. There can still be stuff that is higher tier maths. So more for paper 2 than paper 1, but you can still be asked to draw a tangent on a curve and calculate the gradient, and that's definitely higher tier maths. Okie doke, so this one is not for foundation tier, but if you're taking higher tier, you need to know what a mole is. So basically, one atom is way too small for us to measure the mass of. So rather than just measuring one mass on its own, we measure a kind of multi-pack, and that multi-pack is called a mole. So when we say that the relative atomic mass of sodium is 23, what we mean is that 1 mole weighs 23 grams, and that's compared to a kind of gold standard isotope, which is carbon-12. So this mole is just a big number, right? You understand that if I say a dozen, that means 12. And if I say a million, that means 1 with 6 zeros after it. So if I say a mole, that means 6.02 times 10 to the 23, which is also known as Avogadro's constant or Avogadro's number. Yes, you are supposed to know that number. Are paper 2s harder than paper 1s? Not for chemistry. For chemistry, I definitely think the paper 1 is harder. I think for biology and physics, it's the other way around. But chemistry, quantitative and structure and bonding are way harder than anything that's in paper 2. Okay, so if we know that 1 mole contains 6.02 times 10 to the 23 atoms or molecules or ions or whatever the particle is that I'm looking at, then I can therefore say that half a mole contains half that many particles, right? Think like you're comfortable with the idea of there being 500,000. So you can be comfortable with the idea of there being half a mole or 0.7 of a mole or whatever it is. So if I look at the periodic table and I look at the relative atomic mass of any element, I can say that that many grams of that element will contain the same number of particles. So 12 grams of carbon has the same number of atoms as 1 gram of hydrogen or 16 grams of oxygen or anything else like that. So let's say I want to know how many moles there are in 483. It's time for my favourite equation. Mass is Mr. Mole, which we can rearrange to make be the number of moles is the mass divided by the MR, or actually it could be the AR. It's just the relative mass. But I find mass is Mr. Mole trips off the tongue in a way that mass is R mole doesn't. So I can substitute in or rearrange, whichever way around I prefer. So 483, which is the mass they've given me in the question, divided by the relative mass, which is 23, gives me 21 moles. Right, talk amongst yourselves. I need more water. And she's back. Right, okay, so this is where it starts to get a little bit complicated. And I would say at this point that there are a number of different ways that you can do the next couple of calculations. And the most important thing is that you don't mix and match them. So if you already know a method that works for you, then stick with the method. Okay, so let's say that we start off with a question where we're asked how much aluminium could we make from 510 grams of aluminium oxide. First thing you're going to do for me is housekeeping, because it is so easy to waste 10 minutes doing the wrong calculation. So in the question, they've said 510 grams of aluminium oxide. So you write 510 by the aluminium oxide. And then they've said how much aluminium can you make, so you do a question mark there and you cross everything else out. And that way you don't accidentally waste time figuring out what the relative formula mass of potassium oxide is and working out something for that because you misread the question. Okay, so next up, you're going to work out the relative masses of the things that you're interested in. So we can work out that for aluminium oxide, it's 102, and for aluminium, it's 27. So technically speaking, it's AR for aluminium because that's just an element, but it doesn't really matter. If you wrote MR, that will be fine as well. Now, worth pointing out that relative mass is always for 1 mole. So it doesn't matter that it says 2 lots of aluminium in the equation. We're going to get to that 2. We're going to use that coefficient, but we're not using it yet because relative mass is always for 1 mole. So this is one of the points where some people teach it in a weird, dodgy way that makes no sense. And if you mix and match, you're going to end up doubling twice or halving twice or doing something. How did I get the 102? Okay, so Al2O3 has 2 aluminiums in, and aluminium has a mass of 27. You have a periodic table, so you will be able to look that up. And then it has 3 oxygens in, and oxygen has a mass of 16, so 3 lots of 16. And if I add all those up together, I get 102. You try talking for 3 hours solid and see how well you do. Okay, so next up, we're going to work out the moles of the thing I know the mass of. So here I know the mass of aluminium oxide, so I'm going to work out the moles of that. Now, it's up to you whether you want to rearrange or substitute. Either one is absolutely fine. So here I've just substituted in, so 510 is 102 times my moles. Then I'm going to divide both sides by 102. And I'm going to get 5 is the moles, and that's the moles of the thing that I started off with. No, you do not take the coefficient, so that the big number at the front is called a coefficient, and you totally ignore it at this stage. We're going to use it, but we're not using it yet. Okay, so then we're going to look at these coefficients. Now, I've just drawn in a bright blue 1 in front of the aluminium oxide, because we know that chemists are lazy, we don't write the number 1, but it's just so that when I do my calculation, you can kind of see where it's coming from. So I know that I've got 5 moles of aluminium oxide, and what I'm going to do is I'm going to divide by the number of moles of the thing I have, and times by the number of moles of the thing I'm trying to get. So that's where the 2 comes in, and then I'm going to end up with 10 moles. Okay? So some people teach it in a weird way where instead of working out the relative atomic mass of aluminium, they do the doubling at that point. I don't, because I teach A-level, and if you did it that way at A-level, you wouldn't get your marks. But the point is, if you've doubled it up there, you can't also double it down here. So just watch out for it. So once I know I've got 10 moles of aluminium, I can go back to my masses Mr. Mole equation. And I can do 27 times 10 and I get 270 grams, and that will be my final answer for that question. So if you want to, I don't know, take a quick screenshot or something, those are the steps I went through. So 1 was your sort of housekeeping, writing things down, crossing things out, making sure you don't make silly mistakes. 2 is write down the relative masses of the substances. 3 is calculate moles of the substance that you do have the mass of. 4 is use the coefficients, and 5 is calculate the mass of the substance you're trying to calculate. Right, so the mass was 270. You're not using Avogadro's constant unless they ask you something about a single atom or a single ion. Because we know that the relative mass is the mass of 1 mole. So if I know that I've got 10 moles, then I'm going to do 27 times 10. Okay, so next one is just for the triple scientists, percentage yield. So this is basically about how good is your recipe. What proportion of your ingredients went into the useful product? So it's never going to be, wait, I just said a totally wrong thing. I'm so sorry, I got distracted by the chat. Right, ignore me. Percentage yield. How good was your method of making this thing? So it's never going to be 100% because there's always going to be products left on the walls of the container that you've done your experiment in. So like if you imagine when you, I don't know, make some copper sulfate, you've got like little bits of powder and little bits of crystals left in the beaker. And so when you try and scoop it all out, you don't get 100% of it. There's a bunch of other reasons as well, but to be honest, that is your biggest one. So I would just focus on that. So if I was expecting to make 100 kilograms of ammonia and I actually only made 70, I'd do 70 divided by 100 and turn it into a percentage. It would be 70%. Yes, percentage yield is only triple. Came as a surprise to me too. Okay, next up, concentration. So combined scientists, you are back in the room, even if you are doing foundation tier. So concentration is a measure of how many particles are dissolved in a set volume of a solution. One to watch out for is that the volume is very, very, very often given in centimetres cubed, not decimeters cubed, but you need it to be in decimeters cubed. So you need to convert there by dividing by 1,000. Now, if you're doing foundation tier, combined science, the only units you need are grams per decimeter cubed. Now, these are great units because they pretty much always, if they ask you to calculate concentration, they tell you what units to use, and therefore you don't need to remember this formula because the formula is grams divided by decimeters cubed, and the units are grams divided by decimeters cubed. So they've kind of told you how to do it. Yeah, I would probably say something like not all of the product was extracted, but if you wrote some of the product was left on the beaker, then that's functionally the same thing. So I would still give you the mark for it. Okay, so if you're doing higher tier, then you do also need to be able to complete calculations using moles per decimeter cubed rather than just grams per decimeter cubed. And it's very likely that would involve combining your concentration calculation with the masses Mr. Mole that we already talked about. So something like, oh, now I'm going to think of something soluble. We give you 585 grams of sodium chloride, and then we dissolve it in this. What's the concentration in moles per decimeter cubed? So first you have to work out how many moles that is, and then you have to do your division by volume. Okay, so sometimes they will ask you to convert between a concentration in grams per decimeter cubed and a concentration in moles per decimeter cubed. And this isn't mentioned anywhere in the spec because their argument is if you can convert from grams to moles, which you definitely can, then you can convert from grams per decimeter cubed to moles per decimeter cubed. Because it's the same conversion. You just ignore the decimeter cubed and pretend it's not there. Okay, next up, this is my year 11s know this is my least favourite bit of basically the whole GCSE. If you are given an equation to balance and they give you the masses of everything. So what you're going to do is you're going to write down what the relative mass of everything is. So 56, you just read off the periodic table. 35.5, you read off the periodic table and you double it because it says Cl2. And then we can put those together to give us a relative formula mass of iron chloride as well. Then we use masses Mr. Mole to work out the moles of each thing. And then if we're doing a balanced simple equation, we want the simplest possible whole number ratio. So 464 becomes 232, and therefore my balanced equation would look something like that. Okay, limiting reactants, everybody's least favourite. So in every chemical reaction, there is one reactant that is going to run out first, and that is the limiting reactant. And the one that is not the limiting reactant is called the excess. Now, first thing you're going to need to do, the first 2 marks are going to be working out the moles of both of those reactants. So even if you can't remember how to do this, you can get a mark for working out the moles of each one. But then it's a little bit complicated knowing which one is limiting because you don't necessarily need the same amount of them as each other. So you need to be looking at your symbol equation to figure out how to do this. So here's what we're going to do. First up, we're going to calculate the MR for everything that we know the mass of. Then we're going to work out the moles. Then we're going to divide those 2 moles by each other to make a ratio. And then we're going to compare that to the coefficients in the equation. So here's an example. 72 grams of magnesium reacts with 64 grams of oxygen. First up, write down the relative masses of those. So magnesium is 24, you read it off the periodic table. Oxygen, 2 lots of 16, 32. Next up, work out your moles of each one. So we had 72 grams, 72 divided by 24 is 3. Likewise, we get 2. So that gives me a 3:2 ratio. So if I divide both of those by the smaller number, then I get 1.5 to 1. So now I've got a ratio of 1.5 to 1. I'm going to look back at my equation and say, is that good enough? Is that enough magnesium? And no, it's not, because the equation tells me that I need 2 moles of magnesium for every 1 of oxygen, and I don't have 2. I've got 1.5. Now, if I did that same calculation and I got 2.2 to 1, then I would say, I've got too much magnesium. So magnesium would be excess and oxygen would be limiting. But here, I've got not enough magnesium, so the magnesium is the limiting and the oxygen is the excess. And then if you are asked in like a really nasty question, if they then ask you to go on and work out the yield of one of the products, you're always going to use the limiting reactant. Okay, then atom economy, which I accidentally started talking about before. Sorry. So this is the one about how good is your recipe, like what proportion of your reactants actually end up in your products. This one can be 100% if you are doing a reaction that only has one product. So reactions that have high atom economy are good because they save resources, they save energy, and they ultimately save money. All right, titration. Everybody's favourite required practical, unless they do combined science, in which case it's not their favourite required practical because they haven't done it. So you should be confident naming the equipment. Last year there was a question where you needed to specify that you would measure out the reactant in the conical flask using a pipette, and lots of people didn't know that, so make sure you know that one. Make sure you know that you're using a conical flask so that you can swirl it and the solution doesn't splash out. Conical flask should be on a white tile so you can clearly see the colour change. You should talk about measuring your volumes at eye level. And when you write down your method, make sure that it actually makes sense and it actually works. You should be able to talk about how you add an indicator so that you can identify the first permanent colour change. And either last year or the year before was the first time that they'd asked for the name of an indicator. So phenolphthalein is everyone's favourite, even if you can't spell it. You can't use universal indicator because you need something that is going to suddenly change colour. And universal indicator doesn't, it's just a rainbow thing. So phenolphthalein is good, methyl orange is good. Yeah. Anything else like that? Oh yeah, so with titration, we're going to carry on doing titration until we have concordant data, which is data within 0.1 centimetres cubed of each other. And also just make sure that if you're writing a method that you do say that you're going to write down the volume, because very often people will say something like, oh, we add the acid to the alkali until it changes colour, and then they just stop writing. And they don't actually say, from the burette, read down the volume that's been, read and write down, sorry, the volume that's been added. Yeah, so just make sure that you are actually writing a method that would allow anybody to do it. Yes, for people who are asking, oh yeah, I suppose my required practical banner has covered up the bit that says GCSE Chemistry only, but you can tell because it's bright green at the top. For combined, you have got 3 required practicals. Okay, so in terms of calculations, first up, work out the moles of the thing that you have 2 pieces of information about. So there's one of the solutions, you have the concentration and the volume. So convert the volume and then times them together, that will give you the moles. Then look back at your symbol equation and work out the moles of the other thing, and then divide by the volume that you're left with. So here is an example. So we've got a titration going on with some sodium carbonate and some nitric acid. So first thing, I've marked it in blue so it's really obvious. You have the concentration and the volume about the sodium carbonate. So we're going to convert the volume to 0.025 and then times them together. That gives me my moles of sodium carbonate. Then I'm going to go back to my simple equation, and I can see that for every 1 sodium carbonate, I've got 2 nitric acid. So I'm going to double it. And then I'm going to go back and use my volume. Again, I need to convert it to decimeters cubed. So I'm going to divide by 0.0302, and I'm going to get my concentration. And watch out for the fact it's very, very likely they're going to ask you for a specific number of significant figures, because 20% of all the marks in GCSE chemistry have to be for math skills. So things like standard form significant figures are really, really likely to come up. Okay, also, just for the triple scientists, you need to know that 1 mole of gas is going to take up 24 decimeters cubed of room under room temperature and room pressure. So you can use this to do full calculations. Like if I say 12 decimeters cubed of propane, I can go, oh, 12 divided by 24, that's half a mole. And then I can look at my equation here and say, okay, so it's going to react with 5 times as much oxygen, which is going to be 2.5 moles, and then 2.5 times 24 is 60. But I actually don't need to do all of that, because I know when I'm talking about volumes, 1 mole takes up the same volume regardless. So I can just say, oh, if I need 5 times as much oxygen, the volume is going to be 5 times as big. And 5 times 12 is 60. So that would be a way to speed it up a little bit. Right, Unit 4, with an hour and 10 minutes to go. You can totally do this. So, Unit 4 starts off with looking at the reactivity of metals. So you need to be able to describe 5 different general reactions and talk about your observations, which means things that you can see or you can detect. And you're using those observations to put metals in order of reactivity. So the first thing we said is that metals react with oxygen to form metal oxides. So we can give you the name of literally any metal, and you can use that to make a little word equation. And remember, if they ask you for a word equation, it has to be a word equation. You can't just decide to use symbols because you fancied it. They're not like inherently better or something. You need to do what they ask you to do. So next up, we can say that metals will react with water to form metal hydroxides and also hydrogen. So it might help you to remember that a hydroxide has a high pH, so it's an alkali. Also, when you add metals to water and you see all those bubbles, that's the hydrogen being produced. And we can use our... Oh, I missed a bit. Yes, high pH. We can use our observations to help us put metals in order of reactivity. So if we did these 2 reactions, we would see that the potassium on the left had a lot more bubbles. Therefore, we would say that potassium was much more reactive. Loving the summary of the required practicals. Just FYI, the blue crystals are one of many thousands of different crystals that you could make for that practical. Most of you would have done copper sulfate just because it looks nice, but you don't have to do copper sulfate. This is no longer triple. Filtration is not a required practical. Fractional distillation is not a required practical. That's why you didn't do it yourself. Okay, so then we get... we said we get these bubbles, and we also mentioned that hydrogen, you can prove that it's hydrogen by setting fire to it, and it burns rapidly with a squeaky pop. So it's not, you can't say, do the squeaky pop test. That's not a thing. I mean, it is a thing, but the exam board don't think it's a thing. So you need to talk about setting fire to hydrogen in order to test it. Definitely hydrogen. So next up, we can say that metals can react with acids to make salts and also hydrogen. And this time around, it gets a little bit more complicated because we need to actually start naming them. So there are 3 named examples of strong acids that you are supposed to know about. You are supposed to know their names, you are supposed to know their formulae, and you're supposed to know what salts they make. So for instance, if I were to take some calcium and react it with hydrochloric acid, I would make calcium chloride. Or if I'm trying to make copper sulfate, I want to think which of those acids sounds like copper sulfate. Oh, it's sulfuric acid. So that's the acid that I'm going to pick. Then we start getting into our required practical territory. So we're going to use an insoluble base, which is something that can neutralize an acid, and that could be a metal oxide, or it could be a metal carbonate. So firstly, we're going to think about these metal oxides. So when we had a pure metal and we put that in acid, we got a salt and hydrogen. Now the metal oxide has just got a little bit of extra oxygen. So we're going to have the salt and then water. So that little bit of extra oxygen has stuck onto the hydrogen and made it into water. And then metal carbonates react in the same way, except that the difference between an oxide and a carbonate is that it has an extra carbon atom and 2 extra oxygen atoms. So we also release carbon dioxide. And remember, you could test for that carbon dioxide by bubbling it through lime water, and it would turn it cloudy. So this is, I mean, it's everything. So this right now is combined all the way down to foundation. Whenever the things at the top of the screen go pale and it says higher tier only, that's for higher tier. And whenever they go green, that's for triple. Okay, so this is the first required practical for the combined scientists. And it's a really, really common one to come up. Sorry about all the ticking. My colleagues have started texting me to ask how it's gone. No, guys, it's still going. Okay, so this picture is copper sulfate, which is the blue crystals that somebody in the chat mentioned earlier. But you could be asked to make a pure dry sample of any of the thousands of different ionic salts that we could make in this way. So your first job is to pick your appropriate acid. So if you're making something sulfate, it's sulfuric. If you're making something chloride, it's hydrochloric. If you're making something nitrate, it's nitric acid. They are the only 3. Okay, so it's like a multiple choice question. Which one of those 3 acids is appropriate? Then you're going to heat up that acid, and that's going to speed up the rate of reaction. And then you're going to add an excess of a base. So that base needs to contain the metal that is sort of the first name of your salt. Like if you're making copper sulfate, you would use copper oxide or copper carbonate. You wouldn't use, I don't know, magnesium oxide. And if they might specify in the question, oh, you have to use a metal oxide, but if they don't, you can use either one. I always use the carbonate because that way you get lots of nice bubbles and it's just a bit more interesting to look at, but you can use either. So once you've added an excess of base, you will know that you've added an excess of base because you'll be able to see a solid on the bottom of the beaker. And then we're going to need to filter it to remove that extra base. And then you're going to evaporate most of the remaining water, not all of the remaining water, because if you evaporate all of the remaining water, then you won't get crystals, which is the point of the practical. And so you can't use a Bunsen burner on its own because it is too hot. So you can use a Bunsen burner to make a water bath, but if you're going to say that, you have to explain in quite a lot of detail what you're doing. So it's much easier to just say, use a hot water bath. Or use an electric heater, because those are ways of gently heating it until most of the water has gone. And then we're going to leave it to crystallize. Okay, so there's a little list of metals that you need to be able to put in order of reactivity, but luckily it's not the whole reactivity series anymore. And you should be able to talk about how unreactive elements like gold are just found in rocks as the element, and things that are less reactive than carbon, so iron and zinc are the big ones, can be extracted by displacement with carbon. You should be able to talk about what's been oxidized because it's lost electrons and what's been reduced because it's gained electrons. I'm sure you all know the mnemonic oil rig to help you to remember that. No, you can't use copper sulfate as a base because it's not. You have to be using a metal oxide or a metal carbonate. Okay, so here my metal starts out just as an atom and it's losing 2 electrons to become magnesium 2+. It's lost electrons, therefore it's been oxidized. Meanwhile, hydrogen was hydrogen ions, has gained some electrons, so that's been reduced. You should be familiar with ionic and half equations as well for describing those. So for your ionic equation, you just split apart every ionic compound that is in your symbol formula, symbol equation, and then get rid of anything that doesn't change. So in this example, chloride ions are the same on the left and the right, so they're not interesting, so we just miss them out. And then your half equations we'll get onto a little bit more when we do some electrolysis. Okay, so next topic here is neutralization. So you should know that the pH scale is called the pH scale because all acids contain hydrogen ions, which they release when they dissolve in water to form aqueous solutions. And this is a process called dissociation or ionization. And then soluble bases or alkalis release hydroxide ions, which are OH- ions, when they dissolve in aqueous solutions. Again, this is a thing that got shouted out last year, that people knew about the importance of hydrogen ions, but they didn't say when dissolved in aqueous solution. If you meant copper oxide, then absolutely. So the pH scale goes from 0 to 14, and the high numbers are for the hydroxides, whereas the low numbers are for the acids. and at room temperature, pH 7 is neutral. And the hydrogen ions and the hydroxide ions from the acid and the alkali can join together to do a neutralization reaction, which we can represent with this ionic equation. Okie doke. So pH is an exponential scale, not a linear one. So that means that for every single number you move on the pH scale, the concentration of hydrogen ions changes by a factor of 10. And actually, it's a negative exponential scale. So as pH increases by 1, there are 10 times less hydrogen ions and the concentration drops by a factor of 10. So if I went from pH 1 to pH 4, that would be 1,000 times less hydrogen ions in the same volume. So then, finally, for this pH topic, we need to talk those strong acids. So hydrochloric acid, sulfuric acid, and nitric acid are completely ionized in water or in aqueous solutions, which means that as soon as they dissolve, they give up their hydrogen ions. And then if it's a weak acid, then it's only going to slightly or partially ionize. So lots of those molecules hang on to their hydrogen ions and don't give them up. And so that means that if we've got two solutions of a strong acid and a weak acid at the same concentration, then the weaker acid will have a higher pH. Okay, we got to electrolysis. So electrolysis means splitting up ionic compounds called electrolytes into their elements using direct current. So the electrolyte needs to be melted or dissolved because otherwise, as we said in Unit 2, the ions aren't free to move. So remember, during electrolysis, we are always talking about mobile ions, never delocalized electrons. And we call the positive ions cations and we call the negative ions anions. So once the electrolysis starts, the ions are going to move in response to the charge, with the positive cations being attracted to the negative cathode and the negative anions being attracted to the positive anode because opposite charges attract. When the ions reach the electrode, electron transfer takes place and the ions are discharged. So that means they stop being charged and they turn back into atoms. So this could be the reduction of cations or the oxidation of anions. If you're taking higher tier only, check out that the header has gone pale, then you need to be able to express those redox changes using half equations. So here, my aluminium 3+ ion gives 3 electrons to turn back into aluminium atoms. And so that's an example of reduction. Why is it called ionic equation when it's a covalent molecule? What covalent molecule? There haven't been any covalent molecules in those ionic equations. So if it's a metal and a non-metal, that's going to be ionic. And you are not going to be writing any ionic equations for any covalent molecules. Where do we get to? So here are some oxide ions discharging, and that will be an example of oxidation. So look out for the fact that an oxide ion has a 2- charge. There's going to be 2 of them for an oxygen molecule. And so we've got 4 electrons in total being lost. Okay, doke. So you need to be able to predict what products are being made as part of electrolysis, and that's really easy if the electrolyte is molten. This topic is electrolysis. That's why it says electrolysis at the top of the slide. Or if you mean what unit it's from Unit 4, chemical changes, which is why it says that at the top of the slide. So if it's a molten electrolyte, it's really easy. The first word of the electrolyte, which is the name of the metal, is what is being produced at the negative electrode. So aluminium, magnesium, copper, zinc. Simple. Then slightly more complicated, at the positive electrode, the sort of surname of the electrolyte, the second word, that's what's going to be discharged, but that's not the same thing as the product that's being made. So oxide gets discharged, but we can't make oxide. What we make is oxygen. And then likewise, we make bromine and sulfur and chlorine. Okay, so for a molten electrolyte, which is all you need to know about if you're doing foundation combined science, the negative electrode is just the name of the metal, and the positive electrode is just the name of the non-metal that it came from. So aluminium is a really economically important metal, and it's like a named example of electrolysis. So one of the odd vagaries that you should know about is that something called cryolite is added to the electrolyte, and that's done because it's going to lower the melting point so that a lower temperature can be used to melt it. Now we're still thinking sort of 900 degrees C, right? It's not cool, but it's cooler than it would be if the cryolite weren't added. So during that process of electrolysis, the oxide ions are going to move to the positive anode, and then the aluminium cations are going to move to the negative cathode, and that's where they're both going to be discharged. Now this is a really expensive process because it takes a huge amount of energy to melt the electrolyte, also the electricity to do the electrolysis, and also because these electrodes are going to wear away. So the anodes are made of graphite, which is a type of carbon, and because it is so very, very hot, graphite is actually pretty unreactive, but at 900-ish degrees C, pretty much everything reacts eventually. So when the oxide ions are discharged and they make oxygen molecules, the oxygen molecules react with the carbon to make carbon dioxide and therefore wear away. Now, if you've got electrolysis of solutions, oh, I missed it out, then as well as the ions from the electrolyte, you're also going to have hydrogen ions and hydroxide ions from the water. Okay, so first up, at the cathode, your most reactive cation is going to stay in solution. And that means that there are only 5 possible products that you can make. So either you're going to make hydrogen, or you're going to make copper, silver, gold, or platinum. Now, I find that jewellery metals is a really good way to think of what they are, but it's not something you can say in the exam. So what you would be saying in the exam if they were asking you, say, why is copper produced? You would be saying copper is less reactive than hydrogen. Or if they were asking you why potassium is not produced, it's because potassium is more reactive than hydrogen. But just as a way to remember it, jewellery metals works quite nicely for me. Okay, so before we talked about our negative electrode, and at that point we said that it was going to be just the name of the metal, but now we can't do that anymore. So now we need to think, is it more or less reactive than hydrogen? So aluminium is more reactive than hydrogen, therefore we just make hydrogen. Magnesium is more reactive than hydrogen, therefore we just make hydrogen. Copper is less reactive than hydrogen, so we make copper. Zinc is more reactive than hydrogen, so we make hydrogen. Then our second rule is that if there is a halide ion, so halide ions come from group 7, then that is going to be discharged. Okay, so bromide comes from group 7, so we make bromine, and chloride comes from group 7, so we make chlorine. But nitrate and sulfide, they are no good to us. So the third rule is that if we don't have a halide, then we're going to have a hydroxide ion being discharged, and that's going to produce oxygen. Technically, it's going to produce water as well, but since the whole thing is happening in an aqueous solution, we don't really care about a few more molecules of water. So we're now going to have oxygen produced by the aluminium nitrate and the copper sulfide. Now, there is one half equation I would definitely recommend memorising, and it's this one, because it's probably the only one. If you are someone who's quite good at chemistry and you're feeling quite confident for the exams, it's the only one that I wouldn't trust yourself to remember under pressure in an exam. So 4 hydroxide ions, when they discharge, produce 1 molecule of water, 1 molecule of oxygen, 2 molecules of water, and 4 electrons. Okay. Right, final topic, Unit 5. So we know that energy is conserved in chemical reactions. We've already talked about the fact that mass is conserved in chemical reactions. So you know that conserved just means that nothing's changing, nothing's being created, nothing's being destroyed. So we can split reactions into exothermic and endothermic. So exothermic reactions transfer energy to the surroundings. In other words, some of the chemical energy that was stored in the bonds of those molecules is then given out, and it's now thermal instead. And so that means that the surroundings are going to heat up, and you could measure that with a thermometer, and you would find that the surroundings got hotter. So there are some examples you're supposed to know about: combustion reactions, in other words, fire, many oxidation reactions, and also neutralization reactions where acids and alkalis react together as well. We use these for self-heating cans. So if any of you have done Duke of Edinburgh recently, or you've gone camping recently, and you're trying to heat things without access to fire, then it works for those. And also hand warmers, like where you have the little sort of, it's like a ball of jelly and it's got a little metal clicky bit in it, and you click it and then the whole thing gets hot and hard. That's an example of an exothermic reaction. Then endothermic reactions take in energy from the surroundings, so they cool them down because they take the thermal energy that was already there and they store it in the chemical bonds instead. And there are some named examples, and my experience is that nobody knows what these are, even though they are listed in the specification. So thermal decomposition is using heat to break a compound apart, something like copper carbonate. The reaction of citric acid and sodium hydrogen carbonate, I don't think I've ever known a student who knew that one. And then photosynthesis is obviously a biological example where you take in light energy instead of heat energy. And endothermic reactions are used for sports cool packs. In other words, those ice packs in scare quotes that don't actually have any ice in them. It's just a chemical reaction that gets nice and cold. Okay, so then this is our last required practical. So there are lots of different reactions that you could do. It's just reacting solutions. So that could be mixing an acid with an alkali. It could be taking something like copper sulfate and adding some metals. There isn't one named example of a reaction, so you need to be prepared to read the information that the exam board has given you and talk about the reaction that they're asking you to talk about. I do an A-level chemistry video like this. It exists. It's on the YouTube channel, and it's way more polished than this live stream is. Okay, so crucially, with all of these different required practical versions, you're going to be measuring the temperature change. So make sure, if you're writing a method, that you do actually say you're going to measure the temperature change, preferably with a thermometer. And the point of doing that is to determine whether it's exothermic or endothermic, and to what degree. So we can talk about the fact that we use a polystyrene cup and a lid because polystyrene is a better insulator than other things. So last year there was a question about why polystyrene was better than a glass beaker, and lots of people didn't get marks because they just said polystyrene is an insulator. But glass is also an insulator. It's just that polystyrene is a better insulator. So make sure you're making those comparative statements. Oh, that was me throwing my phone on the floor. Ish. You could talk about the fact that if you use a digital thermometer rather than one that's got coloured alcohol in it, then that's going to allow you to have more precise data. And this is a classic example of a practical where you need to talk about having control variables in order to increase the validity of your experiment. So things like the volume of the reacting substances needs to remain the same. Okay, and it's kind of tricky because there's lots of these where you could change one thing, and if you're not changing that thing, then you need to control it. But for instance, if you're not examining the impact of concentration, you should keep the concentration the same. Or if you're not examining the impact of changing the mass of metal added, then you should keep the mass of metal the same. Really, really important. Can you just ban the word amount from your vocabulary for the next 24 hours? Because in chemistry, it has a very specific meaning. It means the number of moles of something. And so that means particularly if a question comes up where they are asking you about changing concentration and you refer to the amount of copper sulfate solution, it doesn't mean what you think it means. So rather than worrying about whether it's right or whether it's wrong for this particular question, just remove the word amount from your vocabulary and replace it with mass for a solid or volume for a liquid. Also, this is a classic example of where they could test some of the math skills. Remember, there's that massive list of math skills that's at the back of the specification that they could test you on. So one of them is about picking an appropriate graph. I'm not quite sure why my line of best fit has appeared early, but never mind. So if you've got data that is categorical, if it goes in categories, then it should be a bar chart. And all of your bars should be the same width. They should also be drawn with a ruler. I think it was last year that the examiner's report mentioned that lots of candidates didn't bring a ruler, and so they couldn't get credit, even though it was very clear that they knew what they were doing. So make sure you have one with you. Also make sure that if it's a bar chart, there are gaps between the bars. And then if you've got some continuous data, so in other words, both of your variables are numbers and they could be any number. It's not something like shoe size where it could only be a whole number. Then we're going to have a scatter graph. Make sure that if you are, it's very rare that they ask you to draw your own scales, but if they do, make sure that they're even, so they're going up in even amounts. I couldn't sort of have 0.2 and then 0.6 and then 1.2. They need to go up by the same division each time. And also make sure that when they ask you to label graph axes, which they do quite often, firstly, that you actually label them with words. There's been a couple of times where they've said label the X and Y axes, and people have put X and Y. And I understand why they've done that, but that's not going to get us marks in a chemistry exam. And secondly, that you remember to include the units. Lots of people will try to abbreviate. So you'll have something like the temperature change in degrees C, and people will just write temp, and that's not going to get you credit. Okay, so then we get on to a bit of bond enthalpy stuff. So we can say that all chemical bonds store energy, and breaking those bonds requires energy. It takes in energy, and forming bonds releases energy. So the best way to remember which way around it is if you've ever had a play with these mods, these little molecules, when you try to break one of those bonds, you have to put in a huge amount of energy. So remember that process, and that will hopefully help you to remember that breaking bonds requires energy. So we can display this with some reaction profiles. So I'm going to start off with my reactants over here and my products down here. So in this particular instance that I'm drawing, you can see that the products have got less energy than the reactants. I have just totally got distracted by the chat. Let's go back to this a second. So the graph that I've drawn on the right hand side, you can see that that data fits a straight line of best fit. The point of the line of best fit is to allow you to make a prediction about what a different value would be. So say if I was going to do the experiment with a concentration of 0.5, what would I expect the temperature change to be? So your line of best fit should follow the pattern of your data. So if you can put your ruler through it and you can get a straight line, then it's going to be a straight line. But if your data is curving, which is particularly likely to come up in the rates of reaction topic in paper 2, then you're going to do a curve. Right, so we had reactants, we had products, and then in between them, we're going to have a line that goes up and then comes down. It always goes up first, because always the first thing that happens in a reaction is that the reaction takes in energy to break bonds. So the difference between the reactants and the products, that is your overall energy change. I would strongly recommend that if you're asked to draw it on the exam paper, you do like I've done here and do little dotted lines, or just draw it as a straight line with pencil, because if you just draw an arrow that's not quite big enough or not quite precise enough, that makes it very clear to your examiner where you're trying to measure it. And then the activation energy is going from the reactants up to the top. So that would be for an exothermic reaction. If I had an endothermic reaction, then the difference would be that the products would have more energy than the reactants because they've taken some in from the surroundings. That's why the surroundings have got colder, because they've got less energy now, because that energy is now locked up inside the chemicals. So again, my change in energy, my overall energy change, would come from the reactants to the products. And the activation energy is always from the reactants up to the transition state. Okay, so then we get our bond energy calculations. So basically, the rule is add up everything on the left, add up everything on the right, put a minus sign between the left and the right, and the answer is the overall energy change for the reaction. So I personally like to draw out my molecules so I actually have the same number that are in the simple equation. These are very simple molecules, but sometimes you get more complicated molecules and then it's easy to start making mistakes. So here I would say, oh, on the left, I need to break 2 hydrogen-hydrogen bonds and an oxygen-oxygen bond. So I would have those numbers. You are given these numbers in the exam, by the way. You're not expected to remember the values of any of the bond energies. So that would give me 1,370. And then on the right-hand side, I'd say, oh, I need to make these 4 oxygen-hydrogen bonds. So again, I'd write those down. It's obviously fine if you want to write 4 times 464. The reason I do it like this is that particularly with A-level, really complicated molecules, I find it's a really good strategy in exams to cross out a bond as you deal with it. And so as I cross out each one, I would write down 464. But obviously for something like this, that's quite straightforward. You probably don't need to go that far. So I've got 1370 on the left, 1856 on the right, and I would just stick a minus sign in between them, and I would get minus 486. Now, because that number is negative, that tells me it's exothermic. At GCSE, AQA have now said that you don't need to know, you don't need to recognise what a negative number is, but you do need to recognise that if the number for, if the amount of energy that is released by making bonds is more than the amount of energy that's taken in by breaking bonds, then it's exothermic. And personally, I think it's just easier to just say a negative number is exothermic and work it out from there. Yes, this is combined currently. So the other thing they could do that is a bit mean, and that they have done a couple of times in recent years, is give you that overall energy change and ask you to work backwards. So like I said, I like to draw out all my molecules. So I would write it out just like I would before. So the left-hand side is 4 lots of 364 for the hydrogen-sulfur bonds and 3 lots of 498 for the oxygen bonds. Realistically, I would probably work out a total for that rather than just doing it as one big expression. And then on the right-hand side, I've got 4 lots of 464, and I've got 4 lots of this bond that I don't know about. So I would just call it X. And then they've told me in the question that the overall energy change is going to be minus 1034. So from there, I can do a lot of expanding, and I can work out that it's going to be 2128 for X, and therefore the value for X is going to be 532. Now, if you get a question like that, and it's near the end of the exam, you don't have time, you're a bit intimidated, remember, there is going to be a mark for that last division step. So if you can see that there are 4 bonds of the type they're interested in, do some kind of calculation that's got 4x in it, that involves, like, make sure you use every number that they've given you, because otherwise they can't give you marks, and then divide by 4 at the end. Because that 1 mark could be the difference between you getting a 6 and getting a 7, or, you know, you getting a 5 and getting a 6. Okay, last but not least, we are on to chemical cells. So this is just for the triples now. I have got a little bit of general reminders and stuff at the end, but there isn't any more content for the combined scientists. So you should know that cells contain chemicals that react with each other to produce electricity, and the particular voltage that's produced by a cell depends on a number of factors, including the electrode and also the electrolyte. So there are lots of different experiments we could do where we change the metal of the electrodes and see how that affects the voltage. Or a different experiment we could do is we could change the concentration of the electrolyte and see how that affects the voltage. But regardless of which experiment we're doing, we can make a simple cell by connecting together 2 different metals that are in contact with an electrolyte. Now they have to be different to each other because the way that this works is the difference in reactivity between the metals. So if you had 2 bits of metal that are the same metal, then it's not going to generate any current because there's no difference. So the easiest way you can do this, if you're teaching year 7, is to stick a bit of copper and a bit of zinc in a lemon and connect them up, because actually the citric acid in the lemon will work very, very nicely as an electrolyte. But you can also do it with more complicated reactions with sort of salt solutions and things as well. Now, this is a horrible data table, but I'm going to include it because one singular time AQA have given you something as nasty as this, and I want you to be prepared for what is the worst thing that they can throw at you. So, the idea here is this table is designed to show us what is the voltage being measured when we have different pairs of electrodes. So we've got electrode number 1 at the top and electrode number 2 at the bottom. And the bit on the right hand side is greyed out because there's no point in measuring the same pair of electrodes the opposite way around. So if I know that tin versus magnesium would be minus 2.3, then I know that magnesium versus tin would be plus 2.3. So there's no point in doing that experiment because I already know what the answer would be. And then also you'll notice that all of this diagonal is just zeros because that is each electrode against itself. So like I just said, they've got the same reactivity, so nothing's going to happen, and therefore there's just, you know, there's a 0 voltage. Okay, so what we need to do is try and figure out what the reactivity of the metals are and put them in an order of reactivity. So there's kind of no way to decide to start with which is more reactive and which is less reactive. So basically the best way to do it is to pick something that you know is very reactive or know is very unreactive and figure it out from there. So I know that magnesium is a very reactive metal. So I can work out that in this particular table for this particular exam question, a negative number must mean a metal that is on the left is more reactive than the metal at the top. And I can check that I'm right, because if I look at silver, silver is less reactive. I know that's one of my really, really unreactive metals like that. So once I've figured out that, then I can work out some things about the other metals that I'm less sure about. So I've seen that magnesium has a negative value, and so therefore I've said, oh, okay, negative must mean more reactive. So then I can say, okay, so zinc must also be more reactive, iron must also be more reactive, and silver is the only positive number, so that must be the least reactive out of all of those. Okay, so the other thing they could ask you to do is to put these in an order of reactivity and then work out the value for something that they haven't measured. So that's why I've got a random blue rectangle there. This is a value that I'm going to try and figure out. So the easiest way to do this is to just put all of your data on a number line. So if I start off with magnesium, I can see that the distance from magnesium up to tin is 2.3. And I can also see that the distance from magnesium up to silver is 3.2. So basically what I'm doing is I'm saying, what is the difference between those? So then let's just double check that my method works before we do the one that they've asked us to do. So if I look at the distance from silver to zinc, I've put those in different places because I've said, okay, magnesium to zinc is 1.6, that's from the second column. Magnesium to silver, that's 3.2, that's from the second column. And so based on that logic, from silver down to zinc should be a decrease of 1.6. Now, if I look at my table, I can see that that is correct. So my method is clearly working. So then instead of doing from silver down to zinc, I'm going to do from iron down to zinc, which is what they've actually asked me to calculate. So from 2 down to 1.6, that's a decrease of 0.4. So that would be my answer for that's what goes in that box. And then last but not least, we've got chemical cells and fuel cells. Oh, I just realised I haven't looked at the chat for a little bit. No RXN means no reaction. I just can't fit reaction in that box. Oh, thank you for the other people explaining it. Lots of chat about things that are not chemistry. If I asked you about how did you know that the reaction was exothermic, the best thing to say is that more energy is released when making bonds than is taken in when breaking bonds. How many marks would that be? Probably not very many, to be honest with you, because they're only asking you to write down a very little bit. That could even be a 1-mark question, maybe a 2-mark question if you're lucky, which is very mean because it's quite a challenging thing to think about. But in terms of what you're actually doing, you're not doing like a long, complicated calculation. Right, chemical cells. So you should be aware that chemical cells can be wired together in series to produce a battery. And we do that to get a battery that's got greater voltage, so it's more useful. So we know that in non-rechargeable cells and batteries, the chemical reactions are going to stop when one of the reactants has been used up, and alkaline batteries are an example of a non-rechargeable battery. Then in contrast to that, rechargeable cells and batteries can be recharged because you apply an external electrical current and therefore reverse the chemical reactions. Then fuel cells are quite different to chemical cells and batteries. So whereas with a chemical cell or battery, you have a certain volume of fuel that you're starting with, and once it's used up, it's done and it's finished. With a fuel cell, you are continuously supplying it with an external source of fuel. Hydrogen fuel cells are a really common example of this. So in a hydrogen fuel cell, the hydrogen is oxidized electrochemically. So what that means is that instead of setting fire to it so that the hydrogen reacts with oxygen, that would release a huge amount of energy, but it would also be really inefficient because it gets really, really hot and most of the energy is just wasted as heat. And it would also be quite dangerous. So instead, we've got this electrochemical process going on. So the hydrogen comes in and it's split up into hydrogen ions, which pass through the anode into the electrolyte. And then the electrons, and the electrons are going to go through the wire. And on the other side, oxygen comes in and it dissolves in water and it picks up those electrons, and this produces hydroxide ions. And then those hydroxide ions then join up with the hydrogen ions to make water. So overall, we have this electrochemical process where the hydrogen is oxidized and the only waste product is water. But it's worth bearing in mind that even though that makes it sound really great for the environment, you have to get the hydrogen from somewhere. And there are only really 2 main ways of doing that. One is to electrolyze water. So that obviously takes a huge amount of energy. And the other is a reaction using methane. So that is using up a fossil fuel, which we're rapidly running out of. Now, in terms of naming the electrodes, if you have been unfortunate enough to have a chemistry teacher who taught you electrolysis and taught you the panic method for electrolysis, I've got some bad news, because it is exactly backwards for what you need for fuel cells and chemical cells. So you've got two options. One is to just remember panic works for electrolysis and it doesn't work for fuel cells, so flip your equations over, flip your names over. Or the other is to learn that reduction with a C happens at the cathode and oxidation with an A happens at the anode. And that is true both for electrolysis and for fuel cells. In fuel cells, I've seen half equations that involve hydroxide ions and some which do not involve these. Yes, mine has hydroxide ions in. That is the one that is in your spec. If you don't know what panic is, just don't worry about it, because it's just going to confuse you more. It's a way of naming the electrodes, but it only works for electrolysis. It doesn't work for fuel cells. So it's fine to teach it to combined science people, but don't teach it to triples. Okay, so then you could be asked to evaluate and compare the use of hydrogen fuel cells versus rechargeable chemical cells. So first thing, hydrogen fuel cells are continuous, so they just keep going and going and going, whereas rechargeable batteries run out and then need recharging before you can use them again. That means that hydrogen fuel cells maintain their efficiency the whole time, whereas rechargeable cells gradually get less and less good the more you use them. So if you think about your phone battery, when you first got your mobile phone, the battery lasted all day. By the time you're ready for an upgrade, it's probably getting quite low on battery by the time you get home from school, maybe, because every time you recharge it, it gets steadily less efficient. For the hydrogen fuel cells, the only waste product is water, which is obviously not toxic and not dangerous, whereas rechargeable cells very often have heavy metals in them and other quite reactive and quite toxic things. But then on the flip side, hydrogen, quite hard to store, quite hard to transport, highly explosive. Rechargeable cells, nothing dangerous required as a fuel. And then your fuel cells have a relatively low potential difference, so we need to use them as a battery, not just an individual cell, whereas rechargeable cells have a larger potential difference. Okay. So all I've got left then is some sort of general reminders and things. I think it's probably worth me pointing out that this has been like a more extended version with a lot more detail in it, but my basic vanilla version of this presentation is already pre-recorded and on my YouTube channel. So if you missed stuff, or if you want to go back to stuff, or if you were here for the car crash that was Unit 1, I'm still so sorry. I hate technology. You can find that there. But anyway, final reminders. You need to write in black pen. Your exam paper is going to be scanned and blue ink does not scan well. So if you need to, you've still got about half an hour before Tesco closes to go buy yourself some black pens. Likewise, stay inside the box on the exam paper. And if you need to write anywhere else, use the specific extra pages at the back of the exam paper. Don't write in a random place, because your paper is being scanned and your examiner isn't going to know to look for stuff if you've just written it on a random blank page in the middle. Watch out for all your sneaky units. You definitely are allowed to use bullet points for extended response questions, particularly the 6 markers. They're going to make your life easier. They're going to make your marker's life easier. If you get an evaluate question, like for that fuel cells and rechargeable cells, evaluate means compare them and come up with a conclusion. And if you're writing a method, like for the first required practical for the soluble salt, just make sure it's actually going to work. Make sure you've said that you're going to add everything you need to add. Make sure you've said that you're going to change everything that you're going to change, and control things. Unlikely that we've got A-level students in here, bearing in mind it's a GCSE live stream, but you know, we can. Okay, speaking of variables, you modify your independent variable. That is the thing you're changing because you want to know what's going to happen. And that goes on your x-axis, so the horizontal axis at the bottom of a graph. Your dependent variable is the thing you're recording. So you change your independent variable and then go, oh, what happened to the dependent variable? And that goes on the y-axis. Your control variables are to help keep it a fair test. I always tell my class, I am a control freak. So I don't like anything to change. I always have my sort of lilac-y purple PowerPoint. I always have the same seating plan. I always have my exercise book managers sat to my left. because I'm a control freak. So control variables are things that you don't change. Chemical tests are paper 2. This is just general reminders for everybody. And funny you should mention about the errors, because I think it's on my next slide. If you keep doing the same experiment and you get the same results, that is repeatable. If some different scientists do some peer review where they check up on you, that is reproducible. Resolution is the smallest measurement that you can make. Computer-based methods are accurate, rapid, and sensitive. And we talked about this already, but if your data curves, your line of best fit should also curve. Ah, there we go. Okay, so systematic errors are where your equipment is always out by the same amount every single time. So the classic example, I hate using this, but is where people have their scales, like their bathroom scales, and maybe they're a bit embarrassed about how much they weigh, so they change it so that it starts at -1 kilo. And every time that they get on, it tells them that they're slightly lighter than they are. That would be an example of a systematic error. So if you then wanted an accurate measurement, you would have to add 1 kilo to every measurement that you made. And then a random error is just where there's natural fluctuation in the value, or where your equipment is not very precise. So something like, if I measured the room temperature in here, my thermometer might say 19, and then it might say 20, and then it might say 18, and that's just because the temperature is genuinely changing. So for that, you would take multiple readings and then you would calculate a mean. So remember, you're never going to get marks in GCSE Science for just the word repeat. It needs to be repeat it and then calculate a mean. And you might also talk about removing anomalies as well. Somebody asked in the chat about zero errors. So a zero error is just a specific type of systematic error. So actually the systematic error that I described is a zero error, because the issue is with where zero lies. I've mentioned throughout this that there are a number of math skills that can be assessed. So in order to count towards the 20% of the marks that are for math skills, if you're taking foundation tier, the maths has to be hard enough to be taught in Key Stage 3. And if you're taking higher tier, the maths has to be hard enough to be taught in foundation tier GCSE maths. That doesn't mean they can't ask you harder things, but it just means that anything easier doesn't count towards that quota. So this is the full list. I don't think there's anything there that's likely to surprise you. About 5 from the bottom, there's a list of symbols. If you haven't encountered them before, the double less than sign means a lot smaller than. So like if we were comparing the size of a bacterium and the size of you, I might use that less than sign. The sort of alpha fish sign that's 2 from the end, that's directly proportional to. So that's where you have 2 variables where as one doubles, the other one doubles. And it would be a straight line of best fit that went through the origin, it went through 0. And the little wiggly line at the end that's called a tilde sign, and it means approximately equals 2. You've almost certainly done an approximate equal sign where it's 2 lines, but actually listed in the specification for AQA Science is the single tilde rather than the double tilde. So that is the whole lot. Thanks very much for watching, folks, and good luck with the exams.